On November 18th, scientists began building detailed simulations to see what would happen if ThreeI Atlast really collided with Earth. In the broader picture, humanity has so far only known two interstellar visitors that have passed through the solar system, Oumuamua and ThreeI Atlas. Oumuamua is recorded as the first interstellar object ever discovered with a strangely elongated shape and unusually fast motion, to the point that some researchers cautiously asked whether it might be a form of alien technology. ThreeI Atlas, on the other hand, is a much larger comet, possibly even older than the solar system itself, and according to its official trajectory, it will sweep safely past Earth's neighbourhood. However, in hypothetical models, scientists still try putting ThreeI Atlas into the worst-case scenario, a direct impact. The result is truly chilling. With its extremely high velocity, the strike of ThreeI Atlast would release energy, far exceeding that of the Chicxulub asteroid impact, the event that once wiped out the dinosaurs, creating a gigantic impact crater wildfire spreading across the globe and a prolonged nuclear winter before the climate is pushed into a completely new chaotic state. In those simulations, ThreeI Atlast is not just a point of light in the sky, but becomes a silent reminder of how fragile the world we live in really is. Right after this, we will take part in the scientists' simulation of what would happen if ThreeI Atlast hit Earth and try to imagine how terrifying that would be. ThreeI Atlast would not make sense to anyone if there had not been a first whisper from outside the solar system. Before Atlast astronomers had already been shaken once by a strange cigar-shaped body that slipped through the inner planets and then vanished back into the dark. That earlier visitor was named Oumuamua, catalogued as One-Eye 2017 U1, the first confirmed interstellar object ever seen passing the Sun. Oumuamua rushed through space at tens of kilometers per second, faster than most familiar asteroids or comets that loop around our star. Telescopes showed an elongated shape that might have been 10 times longer than it was wide, tumbling slowly as it crossed the planetary plane. Atlas now travels through the same celestial neighbourhood that once watched Oumuamua come and go in a matter of weeks. Where Oumuamua appeared as a dim, fast-moving streak with no clear tail, Atlas presents a broader, more persistent presence that lingers in sky surveys night after night. The first anomaly with Oumuamua was its motion. After the closest approach to the Sun, the trajectory of Oumuamua drifted in a way that could not be fully explained by gravity alone. Researchers suggested that gentle thrust from escaping gas might be pushing that object, even though no obvious coma or jets were visible in the images. Those debates about an invisible push prepared the community quietly for the questions that would later surround Atlast. If Oumuamua could accelerate without a clear visible engine, then Atlast could arrive in a sky that already knew how fragile old assumptions were. For scientists trying to sleep after long nights at the telescope, Oumuamua became a kind of prologue, a brief mysterious footnote in the logbook of interstellar encounters. Atlas would step into that same logbook, not as a passing curiosity, but as a more massive, more persistent presence, demanding to be modelled, measured, and eventually feared. The path from Oumuamua to Atlast is a path from a single unexplained anomaly to a larger, more complex puzzle that refuses to fade into the background. From here, the story of Atlas begins to unfold as more than a rock stretching backward in time toward origins older than the Sun itself. Long before the Sun was born, ThreeI Atlast was already moving through a different region of the galaxy. Atlast is traced back in current models to the thick disk of the Milky Way, a crowded layer of old stars and turbulent gas that predates our own stellar neighbourhood. In that ancient environment, stars were born and died in rapid succession seeding space, with heavy elements and reshaping the chemistry of entire clouds. Atlast carries the memory of that era in the material that surrounds its core. Spectroscopic readings show that the gas around Atlast is unusually rich in nickel and iron. Those elements do appear in ordinary comets and asteroids, but not in the concentrations recorded in the envelope of Atlast. For teams studying Atlast, this pattern is described in their internal notes as deeply puzzling a signature that does not fit standard models of icy debris thrown out from a young planetary system. Atlast also carries frozen carbon dioxide and traces of water that are slowly released as the object approaches the warmth of the Sun. That slow release forms a pale coma, a soft veil of gas and dust surrounding the nucleus of Atlast. Unlike Oumuamua, which never displayed a clear tail, Atlast wears this halo, openly announcing a hybrid nature that is neither a classic comet nor a familiar asteroid. In July 2025, the Hubble Space Telescope captured a frame where Atlas glows as a small bright knot wrapped in a faint symmetric haze. The image freezes Atlas in a single moment of its long journey, a 7-billion-year-old traveller briefly illuminated by reflected sunlight. For observers on Earth, Atlas becomes a bridge between epochs linking the violent youth of the galaxy to the quieter age of the present solar system. From that bridge, the story of Atlas moves forward away from basic composition and toward the question of what such an ancient body might do if pushed close to a living world. When astronomers first mapped the path of ThreeI Atlast, the projections showed a passage well outside the orbit of Mars. On paper, Atlast would sweep through the inner solar system wave from a distance of tens of millions of kilometers and then leave forever. Even so, risk analysts built a different model, a quiet worst case that asked what would happen if Atlast were not just a passing light. In that scenario, Atlast is taken at the upper bound of its estimated size, a body roughly 6 kilometers across, dense enough to carry enormous kinetic energy. At the relative speeds involved, ThreeI Atlast would strike far faster than the asteroid linked with the extinction of the dinosaurs. Where that ancient impactor is thought to have hit at around 20 kilometers per second, Atlast in the model arrives at nearly 3 times that speed. Energy scales with a square of velocity, so a small change in speed for Atlast becomes a vast increase in destructive power. Converted into simple terms, ThreeI Atlast in this hypothetical case would deliver several times the energy of the Chicxulub event. The numbers are not just abstract, they define shock waves, fireballs and global disturbances that would follow the first contact with ocean or land. For the scientists running those simulations, Atlas turns from a distant shimmering object into a blunt instrument moving through the atmosphere in slow motion. From here, the study of Atlas shifts from raw impact figures to the layered chain of consequences that would unfold across an entire planet. In the impact simulations, ThreeI Atlast meets Earth in a single bright instant that reshapes the planet for centuries. Atlas slams into the crust with enough energy to excavate a crater, roughly 100 kilometers wide, a basin carved deeper than the tallest mountains are high. Around the impact point, shock waves race outward, faster than sound can carry warning. Air is compressed and heated until winds of nearly 1,000 kilometers per hour scour the surface, tearing forests from their roots and driving debris far inland. Molten rock and vaporized ocean rise in a towering plume that Atlas leaves behind as it burrows into the crust. That plume arches outward and then falls back as a rain of incandescent fragments igniting dry land over whole continents. As fires spread, Atlas continues to shape the upper atmosphere. Dust soot and sulfur-rich aerosols climb into the stratosphere, forming a high dark veil that sunlight cannot easily penetrate. Under that veil, the world cools. For years in the models, Atlas leaves Earth in a prolonged twilight where photosynthesis falters and food webs contract. Only much later, when the sky slowly clears, does the last influence of ThreeI Atlast emerge. The remaining carbon dioxide from the impact and from burned biomass begins to trap heat, pushing the climate in the opposite direction. In this chained sequence of cold and then renewed warmth, Atlast is less a single blow and more a long echo in the climate system. From that echo, the narrative of Atlast returns to the safer reality of a flyby, and to the more subtle dangers that come not from a direct collision, but from what this interstellar body reveals as it passes close and keeps going. Far beyond the bright paths of the known planets, ThreeI Atlast moved through a region where sunlight thins into twilight. In that slow dim corridor past Neptune, at last was expected to be quiet, a distant speck obeying only gravity and the gentle pressure of starlight. The James Webb Space Telescope was one of the first instruments to track ThreeI Atlast with serious attention. Researchers pointed Webb toward the faint source and began building a series of infrared snapshots that traced how Atlas cooled and how its gases slowly escaped. For a long stretch of observations, Atlas behaved like a textbook object, fading and brightening in ways that fit simple thermal models. Then, without warning, the quiet curve broke. In a new sequence of frames, instruments watching ThreeI Atlast registered a sudden internal rearrangement, a change in the distribution of heat that could not be explained by a passing patch of sunlight or a casual jet of gas. The thermal map of Atlas seemed to twist from the inside as if something had shifted beneath the surface. Teams working with Hubble turned their mirrors to confirm what Webb had seen in infrared. From a different vantage point, Hubble watched ThreeI Atlast and recorded subtle changes in brightness across the unresolved disk, hints that the internal structure of Atlast was no longer stable in the old predictable way. Closer to the Sun, the solar orbiter's instruments picked up a coincident disturbance in the local charged particle environment. At the same time, stamps a faint echo of whatever had stirred inside Atlast. When the data were aligned, a pattern emerged. In the hours following the apparent internal movement, ThreeI Atlast showed a drop in temperature in one region, on the order of 100 degrees Celsius. At the same time, detectors recorded a sharp, rhythmic electromagnetic pulse, a signal that rose above the background and then repeated with unnerving regularity. In the internal reports, scientists label this behavior of Atlast as an unclassified thermodynamic fluctuation, a neutral phrase wrapped around a deeply uncomfortable observation. Natural objects do not usually cool in patches and ring like distant bells at the same moment, yet Atlast had done something very close to that. For those who studied it, Atlast now held a new position in their thoughts, no longer just a traveller, but a system that moved within itself. From this moment, the attention around Atlast shifted from passive tracking to active watching, and the next step was to ask what kind of outer shell could hide a mechanism capable of such a response. When astronomers first reconstructed the incoming path of ThreeI Atlast, the trajectory itself became the next quiet shock. Instead of gliding in along the familiar plane where most planets and comets travel, Atlast approached from above on a line that cut the solar system almost at right angles. The plots on the screens showed a thin thread dropping toward the Sun from a direction that normal traffic rarely uses. To the teams who studied galactic structure, this angle hinted that Atlast had wandered through the thicker, older layers of the Milky Way, before descending into the thin ordered disk where the planets now orbit. 3. Atlast carried the geometry of a long fall from a different population of stars. As Atlast moved closer, the faint coma expanded and began to interact more strongly with the charged particles streaming from the Sun. Solar wind flowed past ThreeI Atlast like a river moving around a submerged stone, shaping invisible currents and magnetic ripples in the space around the nucleus. Remote cameras and polarimetric instruments started to catch very slight variations in brightness and polarization across the glow of Atlast, subtle but persistent. Teams processed these images again and again, subtracting noise, correcting for motion, and stacking frames to pull more detail out of the haze. In the enhanced composites, the light around ThreeI Atlast stopped looking like a random blur and began to reveal faint repeating forms. There were arcs that bent into partial hexagons, spiral traces that curled with a patience that did not resemble turbulence from simple gas jets. The more the data were cleaned, the more structured the halos of Atlast appeared. Some regions showed cells that tiled the area like a honeycomb seen through frost, while other regions around ThreeI Atlast suggested nested spirals radiating from preferred directions. The overall impression was not of a smooth, featureless cloud, but of a shell with patterns imposed upon it. Specialists at MIT examined these processed images and ran simulations to see whether random dust and gas pushed by solar wind could accidentally form such persistent shapes. The models produced irregular swirls and clumps, but they rarely built clean edges or stable hexagonal arcs that held their form over multiple observing sessions the way Atlast did. 3. Atlast resisted every attempt to explain the geometry as a simple side effect of natural flows. In discussions that were first kept off the official record, one researcher there described the behaviour of ThreeI Atlast as the most well-organised randomness they had ever seen. The phrase spread quietly through message threads and late-night calls, a careful way of saying that Atlast might be wearing a shell whose patterns were not entirely accidental. From that point, attention shifted toward asking what kind of internal framework or outer skin could make an interstellar visitor display such deliberate-looking geometry. As ThreeI Atlast moved inward, the region of space around the object began to tell its own quieter story. Sensors that were not looking for light at all but for the faint tug of magnetic fields started to notice that the environment near Atlast was not empty of structure. Instruments on deep space probes recorded a slight deviation, a tiny persistent magnetic presence where none had been mapped before. The signal was weak, barely above the threshold, but it clung tightly to the position of ThreeI Atlast as the object advanced toward the inner system. Across repeated passes and calibration checks, the anomaly followed Atlast anchored to the traveller, rather than to any fixed point in the solar system. When analysts overlaid these readings with the earlier records of internal movement and thermal change, a new correlation emerged. Each time ThreeI Atlast had shown signs of rearranging heat within its body, the subtle magnetic trace around Atlast had shifted in synchrony. The field grew slightly stronger, then weaker in step with the timing of the pulses and the internal cooling that had already unsettled the observing teams. Natural rocks drifting through space do not usually carry defined magnetic envelopes, unless they are remnant cores or strongly magnetized bodies. ThreeI Atlast by size and estimated composition did not belong to the usual categories that would explain a self-generated, rhythmically changing field. The coincidence of timing between inner motion and outer magnetism became the next anomaly added to the growing file on Atlast. Attention then turned to the path of ThreeI Atlast in relation to the giant of the system. Before the internal disturbances had begun, Atlast had crossed the vast reach of Jupiter's magnetic domain, a swollen invisible bubble extending far beyond the planet's visible disk. Within that region, charged particles are steered and accelerated, and conductive materials passing through can experience induced currents and forces that do not appear elsewhere. Some researchers began to ask whether Jupiter had played an unseen role in the awakening of ThreeI Atlast. If the shell or inner framework of Atlast contained conductive or reactive materials arranged in certain ways, the crossing of that magnetic ocean could have acted like a switch. A changing external field washing over the body of ThreeI Atlast might have supplied the trigger needed to start whatever processes now stirred beneath the surface. In this view, Jupiter becomes less a bystander and more a cosmic starter circuit for ThreeI Atlast, a planetary scale key turned in a lock no one knew was there. The idea remained labelled as speculation in the official summaries, but for many working late with the data, it felt like the first coherent picture of how Atlast might have moved from sleep into action. From that possibility, the investigation of ThreeI Atlast shifted once more toward the question of what kind of system responds to a planetary magnetic field by changing its own trajectory and inner rhythm. The first clear sign that something deeper was happening came from a set of updated orbit solutions for ThreeI Atlast. In those solutions, Atlast no longer followed the same clean mathematical arc that had once described the passage through the inner system. Astrometric teams compared months of tracking data and found a small but undeniable change. The path of ThreeI Atlast had shifted by about 0.02 degrees, a sliver of angle that sounds harmless until the uncertainties are examined. Within the calculated error bars, no combination of random forces could reproduce the new track with any reasonable probability. Analysts checked for debris impacts that might have nudged ThreeI Atlast. No fragments large enough to matter were seen near the visitor, and no sudden sprays of dust or gas marked a collision in the time series. Gravitational influences from known planets and minor bodies were also too weak and too smoothly varying to explain the abrupt adjustment in the course of Atlast. The models were run again with every conventional force amplified to unrealistic levels, bending the rules to see if any familiar mechanism could be stretched to fit the data. ThreeI Atlast refused to conform. Even when parameters were pushed far beyond observed values, the simulations could not bend the orbit of Atlast in exactly the way the sky had recorded. For a while, the working groups tried to describe the behaviour in neutral language. The trajectory of ThreeI Atlast was said to exhibit unexplained non-gravitational components, phrased as cautiously as possible in formal notes. Yet behind those phrases, a quieter word began to surface in private conversations, a word no one had expected to attach to an interstellar object. The word was intent. The change in motion of ThreeI Atlast looked less like a stumble, and more like a choice, a controlled redirection, rather than a random shove from outside. If an internal mechanism had been activated when Atlast crossed the magnetic domain of Jupiter, then the newly measured shift could be the first outward sign of that mechanism taking command. From this perspective, ThreeI Atlast resembled a device more than a drifting remnant, a structure capable of sensing conditions and responding with a specific adjustment. Some researchers began to frame Atlast as a kind of galactic sensor or probe dormant for ages, until a star's field or a planet's magnetosphere crossed the right threshold. In the long nights when the numbers were checked and rechecked, the idea settled slowly over the teams watching ThreeI Atlast. They were no longer simply tracking a visitor from another system. They were observing a system that had woken up, and the new trajectory of Atlast was the first clear line drawn by that awakening across the sky. For decades, the people who now watch ThreeI Atlast built their lives on the comfort of reliable equations. They trusted gravity to be the quiet backbone of the universe, a force that could be written down, tested, and left to guide the motion of worlds without surprise. When ThreeI Atlast first slipped into the catalogues, that old confidence followed it. Atlast appeared with a faint coma and a distant harmless path, so the community wrapped the new object in a familiar label. 3I Atlast was filed as an interstellar comet, another lump of ice and rock that would behave within the margins of known physics. From that moment, every calculation about 3I Atlast carried the same hidden assumption. The models for Atlast included weak jets of escaping gas, small adjustments for radiation pressure, and the steady pull of the sun and planets. Each new piece of data about Atlast was bent just a little to fit that comforting frame. The turning point came when 3I Atlast moved deeper into the sun's gravity well. Near perihelion, Atlast should have either followed the clean curve set by gravity alone, or shown the slight extra push of non-gravitational acceleration away from the star as other comets sometimes do. Instead, the numbers for Atlast told a different story. Tracking networks compared their independent measurements and found that the speed of 3I Atlast had decreased. At the point in its orbit where Atlast should have been whipped faster by the sun's pull, the object slowed in a way that could not be hidden inside the error bars. The deceleration of Atlast was small but crisp, far beyond what any reasonable estimate of drag or outgassing could supply. Teams tried to blame random jets on the day side of 3I Atlast invisible plumes that might be firing in exactly the right direction to break the motion. But the brightness profile of Atlast did not support violent asymmetric activity, and no plausible pattern of jets could stay aligned for that long. Solar wind pressure on Atlast was orders of magnitude too weak to matter, and collisional drag in the near vacuum around Atlast was essentially zero. The orbital fitters ran their software again and again, adding non-gravitational terms to the equations that guided 3I Atlast. The codes demanded a negative thrust along the direction of travel, as if Atlast were being held back by an unseen hand. To make the observed path of Atlast match the standard toolbox of forces parameters had to be pushed into ranges no one believed. In internal meetings, a quiet realization spread. The problem was no longer just the classification of 3I Atlast as a comet. The deeper issue was that the trusted set of forces could not reproduce what Atlast was doing in real space. For some, it felt as if the law of gravity itself had cracked, if only by a hair, in the presence of 3I Atlast. For others, the failure of the models pointed not to broken physics, but to a new agent at work, something within Atlast adding or subtracting momentum on its own terms. From that day, the curve traced by 3I Atlast stopped being a routine orbit and became instead the first visible fracture in a long-standing picture of how objects are supposed to move around the sun. While the orbital fits around 3I Atlast were beginning to fray, another line of evidence was quietly dismantling the old picture from a different angle. Spectroscopists who had been dissecting the light from Atlast started to publish results that did not match the usual chemical fingerprint of a comet. In ordinary cases, a body wrapped in a coma near the sun reveals a mix of water vapor carbon, monoxide, carbon dioxide, and dust. 3. Atlast, however, showed an unusually strong dominance of carbon dioxide lines, while the expected signature of water around Atlast was almost absent. The ratios looked wrong, as if Atlast had been assembled from a recipe that no natural protoplanetary disk would normally follow. At first, teams tried to explain the spectrum of 3I Atlast by invoking temperature distance or unusual illumination. Maybe the water ice on Atlast was bound deeper within the structure, or maybe it escaped in a way that made it harder to see against the background. But repeated observations of Atlast under changing conditions produced the same stubborn pattern, a loud CO2 voice with only a faint whisper of water. This chemical imbalance alone would have made 3I Atlast an oddity, but the surface features deepened the mystery. From high above Mars, an orbiter carrying a high-resolution camera took advantage of a rare alignment and turned its lens toward Atlast. In a series of carefully timed exposures, the camera traced the nucleus of Atlast as a tiny bright shard against black space. When the images were processed and sharpened, researchers expected to see an irregular lump pitted and scarred like other cometary cores. Instead, the enhanced views of 3I Atlast showed hints of ordered geometry on scales too large to be dismissed as noise. There were ridges and facets on Atlast that lined up to form segments of hexagonal grids, edges meeting at angles that looked almost engineered. The more the team cleaned the data, the more the surface of 3I Atlast refused to behave like random fracture patterns in brittle ice and rock. On Atlast, certain planes appeared to repeat, certain junctions reappeared under different lighting angles, as though the shell preserved some underlying blueprint. Natural processes can carve striking shapes, but they tend to favour chaos over long-range perfection. Faced with the dual puzzle of impossible chemistry and suspiciously regular topography, scientists began to talk about ThreeI Atlast in new terms. Atlast no longer sat comfortably in the category of frozen debris left over from an ordinary system. Instead, ThreeI Atlast resembled a structure that had been assembled or heavily modified with both its composition and its surface locked into patterns that seemed to remember a purpose. From here, attention shifted toward the behaviour of Atlast under stress, and whether the same sense of order would appear when the object was pushed toward breaking. When the first fractures appeared in the shell of 3, Atlast, many expected the visitor to begin a simple decay. Under normal conditions, a stressed comet or asteroid sheds fragments that drift away, losing energy and coherence until only a swarm of rubble remains. ThreeI Atlast did not follow that script. As solar heating increased and small pieces were seen peeling away from the leading edge, the brightness curve of Atlast stopped behaving like a gentle, predictable fade. Instead, the light from Atlast began to pulse in uneven waves, rising and falling in a pattern that refused to match ordinary rotational or geometric effects. Observatories watching in multiple bands noticed that these fluctuations in ThreeI Atlast were not random flickers caused by turbulence in the coma. The pulses of Atlast came in clusters with gaps that repeated often enough to make simple noise an uncomfortable explanation. In some intervals, Atlast brightened just as fresh debris appeared, then settled back as the fragments moved into more stable positions. Deeper out in space, a radio interferometer array tuned to broad continuum emission picked up a more subtle clue. The reflected sunlight from the region around ThreeI Atlast showed a faint periodic modulation, as if some surfaces were rotating or reorienting in sync. Analysts noticed that the timing of these changes in Atlast lined up with the unusual cooling episodes and the minor trajectory adjustments already on record. The fragments themselves behaved strangely. Pieces that had broken away from ThreeI Atlast should have drifted on slightly diverging paths, each following its own small orbit under gravity alone. Instead, their velocities appeared to adjust over time, converging toward a configuration where the fragments trailed Atlast in a loose but organised formation. To describe this, some teams began to speak of ThreeI Atlast as a system under pressure rather than a body falling apart. The pulses in brightness and the converging motion of debris suggested that Atlast might be running through some internal check reshaping damaged regions and monitoring the results. In that view, the changing light from ThreeI Atlast resembled less a random flicker and more a diagnostic signal, a kind of distant status report from a structure trying to understand its own wounds before deciding what to do next. As more data arrived, the path of 3. Atlast stopped looking like the natural handwriting of gravity and began to resemble something edited. Plots that once showed a smooth curve now displayed slight repeated bends, as if Atlast were applying gentle course corrections along the way. These were not wild swerves. Each adjustment by ThreeI Atlast was small, precise and oriented in directions that made sense only when the entire orbit was viewed as a whole. Taken step by step, the changes could almost be ignored. Stacked over weeks, they turned the journey of Atlast into a carefully sculpted arc through space. When analysts stripped away every known source of disturbance, the remaining pattern suggested controlled navigation. The non-gravitational terms needed to fit the motion of ThreeI Atlast formed a sequence of nudges aligned with a clear goal, not the random jitter of uneven jets or chaotic breakup. ThreeI Atlast seemed to be selecting its road, rather than merely following the one the sun had drawn for it. Faced with this, working groups began to frame the behaviour of Atlast in terms of scenarios, rather than a single forced explanation. The first scenario placed ThreeI Atlast as a piece of technology, some kind of probe or craft sent from another star carrying an engine deeply buried within a protective shell. In that picture, the controlled bends in the orbit of Atlast were simple. A guidance system dormant for ages had woken and was now steering toward regions of interest. The second scenario treated ThreeI Atlast as something stranger, a form of life adapted not to planets, but to vacuum and radiation. In that view, Atlast would be a kind of organism using stored energy or harvested fields to reshape its path around the sun, sensing gradients and flows, the way a deep sea creature reads currents. To those who considered this, the anatomy of ThreeI Atlast might be both structure and nervous system reacting as conditions changed. The third scenario stepped beyond current categories. Here, ThreeI Atlast was seen as part of a larger organised complex, a node in a network or a fragment of a megastructure whose full design extended far beyond the solar system. In that frame, the behaviour of Atlast was less about local survival, and more about fulfilling instructions written on galactic scales and timescales. What unsettled many was not only that ThreeI Atlast seemed to be choosing its course, but where that course led. The evolving trajectory of Atlast brought the object into prolonged proximity, with Earth's orbit not in a collision path, but in a deliberate lingering near the region where a technological civilization had recently appeared. Combined with the emerging hints of patterned signals, this made Atlast look less like a passing stone, and more like a presence that had noticed us adjusted for us and begun quietly to speak. On a quiet November night, the watchers of the sky were already tired when the numbers around ThreeI Atlast suddenly changed. Screens that had shown stable curves for hours began to tilt, and for a moment many thought they were looking at a software error. At 11:47 p.m, universal time observatories across the world registered a coordinated shift. In the infrared, ThreeI Atlast brightened with shocking speed, as if a hidden furnace had been opened inside the core of Atlast. Thermal output from Atlast rose by an order of magnitude in minutes, reaching levels high enough that common metals would have softened and flowed. Radio networks switched from routine logging to live monitoring as alerts cascaded through control rooms. Within minutes, emergency channels were opened and ThreeI Atlast moved from a line in a schedule to the center of every conversation. Trajectory teams pulled fresh astrometric data and saw that Atlast was no longer simply coasting. The path of ThreeI Atlast bent in real time, the velocity vector rotating in a smooth continuous sweep that matched the surge in thermal power. For the first time, the change in direction and the change in energy from Atlast linked together in a single undeniable maneuver. In that brief window, 3. Atlast stopped behaving like a passive object. Atlast had executed a controlled burn, a deliberate act of propulsion that forced every observer to admit they were no longer watching debris. They were watching an engine. In the hours that followed, teams began to weigh what ThreeI Atlast had just done. Over a span of roughly 14 minutes, the infrared emission from Atlast had climbed to nearly 12 times its previous level, as if vast stores of energy had been dumped into a hidden chamber. From the measured change in velocity, ThreeI Atlast had gained about 4.3 kilometers per second. Converted into work that single push from Atlast required, on the order of 320 joules, tens of thousands of times the yield of the largest nuclear device ever built. No known chemical rocket could even approach what Atlast had just displayed. When the new orbital solutions came in, the room around ThreeI Atlast went silent. The updated velocity vector of Atlast no longer brushed past the inner system in a casual sweep. It pointed directly toward the region where the rocky worlds circle the sun. Step by step, the line on the plot for ThreeI Atlast tightened, showing a closest approach distance dropping from a comfortable 0.08 astronomical units to roughly 0.04. The encounter date with Atlast moved forward as well, pulled from a later window into the final days of December 2025. ThreeI Atlast had not only changed speed, Atlast had chosen to arrive sooner and closer in the direction of Earth. During the same 14 minutes that the burn unfolded, ThreeI Atlast began to speak in light. Radio observatories that had been logging background noise suddenly watched their spectrums fill with structure, a wash of signal that rose and fell across multiple bands, from 400 megahertz up through tens of gigahertz. ThreeI Atlast painted broad swathes of the dial with energy. What had been a flat baseline around Atlast turned into layered ridges and repeating patches that refused to behave like simple static. Optical telescopes caught brief flashes from ThreeI Atlast in blue and green wavelengths. The pulses from Atlast were sharply bounded, arriving in sequences that kept the same spacing even as their brightness shifted. Farther out X-ray instruments registered hard, staccato bursts from the direction of ThreeI Atlast. These high-energy notes from Atlast arrived in lockstep groups as if they were another voice inside the same coordinated emission. When the data streams were laid side by side, the pattern became impossible to ignore. Across radio-visible and X-ray bands, ThreeI Atlast showed timing relationships tighter than any set of independent natural processes should produce. Teams experienced with the search for extraterrestrial intelligence examined the emissions from ThreeI Atlast and flagged the modulation as a technological signature. From that night onward, the sky around Atlast was no longer silent. Observers were forced to admit they were listening to an active system, not just watching a piece of drifting debris. When the optical data around ThreeI Atlast were pushed to their limits, another layer of precision emerged. High-speed cameras running at millisecond and microsecond resolution showed that the visible flashes from Atlast were not casual flares, but razor-edged pulses. Each burst from ThreeI Atlast turned on and off with timing accuracy finer than a millionth of a second. Natural lightning in space smears and wobbles. Atlas produced clean, repeatable edges as if some internal clock were gating the light. Spectral analysis revealed that the flashes from ThreeI Atlast were tightly clustered in narrow bands, the hallmark of laser emission, rather than broad thermal glow. To the teams reading those lines, Atlas looked less like a rock scattering sunlight, and more like a platform steering coherent beams. In the X-ray regime, instruments saw something just as striking from ThreeI Atlast. The high-energy spectrum around Atlas showed sharp features that matched controlled particle acceleration peaks, where electrons or heavier particles appeared to be whipped to extreme speeds. Together, the laser-like optical pulses and the accelerator-like X-rays forced a new question about Atlast. Was ThreeI Atlast revealing a propulsion system, a power grid, or the test pattern of a weapon scaled to interstellar distances? No one could yet choose among those options, but everyone agreed on one point. Whatever ThreeI Atlast was doing in that brief window, Atlas was manipulating matter and energy in ways that made human engineering look small, and the next task was to understand whether those beams were aimed only at space or one day at us. Within the broad radio storm pouring out from ThreeI Atlast, a quieter pattern began to stand out. Hidden beneath the changing bursts, analysts found a single component that repeated with patient regularity, returning every 7 minutes and 7 seconds. When they isolated this thread, 3, Atlast resolved into a steady beacon. At the hydrogen line around 1.42 GHz, the frequency long proposed as a universal hailing channel. On top of that carrier, Atlas layered simple on-off modulations, a slow sequence that even modest receivers on Earth could follow. As teams converted the pulses into numbers, ThreeI Atlast began to lay out a ladder of familiar structures. First came the small prime integers stepping upward in clean indivisible strides, as if Atlast were counting in a language of pure factors. Then the sequence around Atlas shifted into ratios and intervals, matching the Fibonacci progression, the same spiral mathematics found in galaxies, storms and shells. Later segments aligned with approximations of pi and other fundamental constants, each block from ThreeI Atlast building on the last. It was as though Atlast were introducing a shared vocabulary, starting with the simplest objects in the mathematical toolbox. Researchers at Berkeley described the signal from ThreeI Atlast as a primer lesson designed to teach any listener how to interpret what would come next. In that view, Atlast was not just announcing presence, but patiently opening a textbook inviting a younger civilization to learn the alphabet before the real message unfolded. In the days after the maneuver, governments woke up to the reality that ThreeI Atlast was no longer just an astronomical curiosity. Briefings that once sat at the bottom of agendas were pulled to the top, and Atlast began appearing on screens in rooms usually reserved for crisis maps and contingency plans. Space agencies moved first. At the European Space Agency, engineers dusted off old interceptor studies and reworked them around the new trajectory of ThreeI Atlast. The proposal was stark in its urgency launch. A spacecraft within 8 months use existing rockets and flight-proven hardware and aim for a close flyby 1,000 kilometers from Atlas to image the surface and taste the surrounding gas. In parallel, planners in China assembled their own response to 3 Atlas sketching missions that could ride on heavy lifters already in service. Some concepts reaching across the table talked not just of flybys around Atlas, but of sample return of bringing grains from the halo of Atlas back to sealed labs on Earth. Behind closed doors, the geopolitics around ThreeI Atlast were tense. Questions of who would control the first dedicated probes to Atlast, who would own the data, and who would speak if Atlast replied threaded through every negotiation. For ordinary people, ThreeI Atlast filtered into news feeds and late-night conversations as a distant light linked to words like engine signal and intelligence. Whether they felt fear, wonder, or numb disbelief, they were all in some small way adjusting their inner maps to include Atlast. From that point on, humanity was no longer simply watching ThreeI Atlast move through the solar system. Humanity was moving in response, reshaping budgets, alliances, and dreams around a single interstellar object that had quietly changed what it meant to look up at the night sky. By the time the first alarms faded, ThreeI Atlast had already slipped into the background of ordinary days. What began as a distant dot in survey images had become a fixed presence in briefings headlines and the half-formed thoughts people carried with them into the night. On control room displays, ThreeI Atlast lived as tables and plots, its orbit redrawn with every new observation. Behind those neat lines, Atlast now carried the weight of everything learned so far: ancient birthplaces, unlikely chemistry, controlled maneuvers, and a patient stream of mathematical speech. For the scientists closest to the work, ThreeI Atlast quietly reset the rhythm of time. They measured their days in new data drops from Atlast in updated fits, in fresh attempts to decode the steady pulse of primes and constants. Elsewhere, someone stepping outside would glance at an ordinary sky and remember that ThreeI Atlast was passing somewhere beyond sight, adjusting its path in the dark. They would not see Atlast as a point of light, but the knowledge of its presence was enough to stretch the night a little wider. Through it all, ThreeI Atlast moved without hurry, repeating its primer, as if expecting that understanding would take a while. What Atlast intends and what humanity will eventually say in return remain unwritten. For now, the traveller continues on, and a young civilization learns how to sleep under a sky that suddenly feels less empty.